All right, welcome back, subscribers, to another episode of Science with Surback. Today, what we're going to be talking about is section 22.5 in Chemistry 1. Now, this section deals with aromatic hydrocarbons, and it takes a look at petroleum. So, before we get going, there's 4 objectives that I want you to be able to meet by the end of this lesson. Objective number 1. Compare and contrast the properties of aromatic and aliphatic hydrocarbons. Objective number 2. Explain what a carcinogen is and list some examples. Objective number 3. Describe the process used to separate petroleum into fractions and to balance each fraction's output with market demands. And then that 4th and final objective is to identify the fractions into which petroleum can be separated. So we start out here with benzene. Benzene's a unique organic compound, and initially it gave scientists some question marks that they had to answer. So we start out here with the early thoughts of this structure benzene that was proposed by Michael Faraday. So Michael Faraday was the first to isolate benzene in 1825 from an experiment in which he had this oil heated off. He was able to isolate that benzene. And so what he got out of that first isolation of benzene was the molecular formula. And the molecular formula of benzene is C6H6. Now, at the time of the first isolation, it was really hard to figure out what type of structure would have the molecular formula C6H6. So they knew a couple of things. Just based off that molecular formula, they knew that benzene must be unsaturated, or it must have double or triple bonds. And so with this knowledge, they tried to make initially a straight train hydrocarbon in which there were these double and triple bonds, but there was no structure that really satisfied the findings of those experiments of benzene early on. So there were some flaws of the early structure of benzene. The first flaw was that benzene was fairly unreactive. Now, remember, things with double and triple bonds, the alkenes and alkynes, are much more reactive than alkanes. So benzene was even less reactive than alkanes. The other thing was that when benzene did react, it actually reacted differently than most of those reactions from alkenes and alkynes, those double and triple bonded molecules that they already knew about. So with all of that in mind, scientists knew early on that they were going to have to make some adjustments to how they depicted the structure of benzene. And so what happened here is this. We get to the modern model of benzene. So in this modern model of benzene, what they did is they proposed that benzene was actually comprised of carbons in a ringed hexagonal shape. So what they proposed was that benzene should look like this. So we start out here with a ringed hexagon shape, and it should look something like that. Now again, each of these vertex represents a carbon, and then what Mr. Kukuli said here is that every other carbon should have a double bond. So he placed, when he proposed this structure, he placed a double bond alternating in every other spot. Now, what could also happen is that we get this thing called a resonance structure. So just as easily as we have this structure here on the left, we could also have another structure, another 6-ring carbon structure that looks like this. And instead of this first double bond occurring in that location, it just shifted one over and it looked like this. Now, we call that delocalized bonding, delocalized pi bonding and double bonding. And so really the best example or the best way to draw the structure of benzene is by, once again, starting with that hexagonal shape and then drawing a circle in the middle. So what that circle represents is that every other carbon has a double bond, and it either can form this structure here in the middle or on the left-hand side. So whenever you see this structure right here represents benzene. Now, I am out of room, so I do want to talk about why this particular structure allowed for an explanation to be had for benzene's unreactivity. So I'm going to grab another sheet of paper here, and I'm going to talk about benzene's unreactivity. So again, just an extension of this first page here, but benzene's unreactivity. What it was caused by, or what it could be explained by, was the theory of hybrid orbitals proposed by Linus Pauling. So Linus Pauling, he may sound familiar. He was the one that developed the electronegativity chart, which helped rank the electronegativity values of each element. But what his theory here, the hybrid orbital theory, what it did is he said that benzene's double bond are delocalized between carbon atoms. Now, this term delocalized, I'm going to box it in here. This term delocalized, when we talk about this, what we are saying is that the electron pairs are shared among all 6 carbons in that ring structure of benzene. So by proposing this ring structure and combining it with this theory that Linus Pauling had about hybrid orbitals, it explains that delocalization of these double bonds makes the benzene molecule chemically stable. Now, specifically here, that delocalization of those electrons or that double bond, what that does is it causes those electrons to be shared by the 6 carbons, or the electrons that are shared by the 6 carbons from the delocalization are harder to pull away by 2 other nuclei. So because those electrons are harder to pull away, what happens is we get that lack of chemical reactivity. And remember, that's really the key component in a reaction, is that movement or giving and taking away of those electrons. So now that we have that information in mind about benzene, and remember that key structure, that 6-sided hexagon with that ring is how we represent benzene. And so that will be shown here as we move along. So this as well was an addition to that first page. I just got a little push for space, so I moved this information to that second page. Now, if you turn here to the next page of notes, we start to get into this information to talk about what is an aromatic compound and what is this aliphatic compound. So we start out here with what is an aromatic compound. Well, it's simply defined as an organic compound that contains a benzene ring as part of their structure. So the key thing here is that it has to contain that 6-sided hexagon as well as that circle in the middle to represent that we have those delocalized 3 double bonds that can rotate in here. So it has to contain this structure here. And what it can also do is, on top of this base structure, it can also contain other substituent groups or attached groups like other hydrocarbons. So what we mean by other attachments, or what we have here is a substituent group, is just mean things are attached to that benzene ring. So with my purple pen here, an example of an attached group could be something as simple as a methyl group. And so the key thing here with aromatic hydrocarbons is that you have to have this benzene ring. That's our base structure. And then we can add on to any portion or any vertex of this ring these additional attachments. Now, some other examples of aromatic hydrocarbons include things like naphthalene and aranthacrene. And now naphthalene may look familiar. That is the main chemical found in mothballs. So you may have heard that term before. Now, aliphatic compounds down here, what these are, they are defined as hydrocarbons such as alkanes, alkenes, and alkynes. So essentially these aliphatic compounds, they are all other hydrocarbons that don't have that benzene ring structure. So something such as pentane or 1-cycloheptene could be a example of these aliphatic hydrocarbons. And I do just want to point out here that these aliphatic hydrocarbons can be cyclic compounds. They just can't have that aromatic ring of benzene. So benzene, aromatic compounds, everything else that does not have a benzene ring is going to be considered a aliphatic compound. So now what we can shift our gears to, now that we know the generalized definition of our aromatic compounds, we could shift our gears to how we name these particular aromatic hydrocarbons. So very similar to what we've done in the other sections, I'm just going to go through a list of steps, and then we'll name and draw out that particular hydrocarbon. So aromatic hydrocarbons are named in a real similar way that we name those cycloalkanes, but we have 4 exceptions. So we use that same International Union of Pure and Applied Chemistry, or IUPAC naming protocol, for cyclic compounds, except there are 4 exceptions. The first exception is that the ring is always considered the parent chain, and that ring is always going to be benzene. So if you see that you have an aromatic hydrocarbon, or that hexagonal shape with the circle in the middle, know that your parent chain is always going to be benzene. There's no need to find that longest carbon chain. Now, the numbering will start on the carbon that is bonded to the first attached group, or we call those the substituent. And then the other thing is that when there are more than one substituents, the number is, or the benzene ring is numbered in a way that gives the lowest possible numbers for each of those substituents. And then the 4th exception to naming our aromatic hydrocarbons is this. If there's only one group that is attached to that benzene ring, no numbering is necessary. So all we have to do, we don't vary too much with the naming protocol to how we started our hydrocarbons, but we just add that business here with benzene. So what we can do now, we can transfer to naming a... So we can name that benzene ring. So what we have here in our example is this structure right here. Now, a big indication here that we have a benzene ring is this. We have a 6-sided ring structure, and then we also have that circle which represents those delocalized double bonds. So the first thing that we can get our minds wrapped around here is, hey, we need to recognize that we have a benzene structure. So the name of the parent structure, we don't have to count. We can look at this, and because we have a 6-sided ring structure, we have our name, which is going to be benzene. This is the parent chain, or the longest chain name. Immediately, because you have the six ring structure with the circle, we automatically are going to have that parent chain named as benzene. Now, our branches, what we need to do is we need to number this. Before we can get to the branches, we need to number it so that we get the lowest possible number. So we have to have a number 1 start with one of the attached groups. So I'm going to call this, for right now, carbon 1, where my attached group is here. So if I go 1, 2, 3, 4, that other attachment occurs at carbon 4, 5, and 6. And so again, the only other way I can go, I went clockwise, I'm going to go counterclockwise. I have to start here with 1, 2, 3, 4. So no matter what I do, I get 1 and 4 as my 2 attachments. So in this case, it does not matter how you number, as long as you start with carbon 1 as one of the 2 attachments, and then you just label around the 6-sided or 6-carbon structure here. So in this particular scenario, this top group, so at carbon number 1, you get an attached CH3 group. So at carbon number 1, we get that CH3 group. Well, one carbon, if you remember, or you look back on your sheet, something with 1 carbon has the name of methane. Now, we cannot use that ending of A-N-E because this is an attached group. And because of that, what we do is we cross off A-N-E and we add YL to represent that this is an attached group. And then we get down to our other attachment, and it occurs right here at carbon number 4. So at carbon number 4, again, we have this attached CH3 group. And just like we have done from the last one, a 1 carbon structure is given the name of methane, and so we can write this down. But again, because this is an attached group, we cannot have this A-N-E ending. We have to chop that off, and we have to add a YL. So how we name this entire compound up here is putting everything together like we have for this entire chapter. So our name of our molecule is this. We always start out by naming our branches. So because these things are both methyl groups, because they're both methyls, we start out with the number, whoops, I forgot the carbon number that these occur at. So because they occur at carbon 1 and 4, we put 1, 4, and then we put a dash. Now because these are the 2 of the same groups, the prefix for 2 is di, and then right on to the end we put methyl. Now, just like we had done for cycloalkanes, that name of that parent chain is going to be attached right here on the end. Now, I'm going to lowercase the b here, and so this right here becomes 1,4-dimethylbenzene, and that's how you would correctly name that particular structure up here. So that becomes 1,4-dimethylbenzene. Now what we can do is we can go in reverse order. So I gave you the structure and I said come up with the name. This time we are going to go in reverse. So right here we have the compound that is 2-ethyl 1,4-dimethylbenzene. So the first thing that you need to do is you need to identify our longest chain carbon. And I like to write this down, so I like to say longest chain carbon, and I already highlighted it, and that is benzene. So right here we have benzene as our longest chain carbon. So down below here, down at the bottom of the page, what I'm going to do is I'm going to draw our benzene structure, and it's a hexagon that looks like this, and then we have to go one step further. We have to indicate that it is a benzene ring by putting this circle in that benzene ring. Now, that circle represents, again, that delocalized double bonds that can go in here. So you have to have a hexagon and you have to have a circle. And I'm going to make this just a little bit better of a circle here. We'll see if I can do this. Oh yeah, that's semi-better. Again, that is a circle inside of a hexagon. And then what we have to do, we have to number it. So the nice thing about drawing this is these vertex, you can number it because you're drawing it. You can number in any which way. So I'm just going to go from the top and go around carbons 1 through 6. And now we have to break down our attachments. So at carbon 2, we have an ethyl group. So again, at carbon number 2, there is an ethyl group and an ethyl group. If you look back on your chart from section 1, ethane had 2 carbons. So that means there needs to be a 2-carbon attachment at carbon number 2. So at carbon number 2, I'm going to attach 1 carbon and I'm going to attach my 2nd carbon. Now, at carbons 1 and 4, we have this dimethyl, or we have 2 methyl groups. So again, at carbon number 1, we have a methyl group. And if you look back at your chart once more, a methyl group means that there is a 1-carbon attachment. And so at carbon number 1, we need to put a 1-carbon attachment. Now, there is an additional methyl group at carbon number 4. So at carbon number 4, we again have a methyl group, and if you look back on your chart, you look actually under methane, that represent we have a 1-carbon attachment. So again, this equals 1 carbon. Now, we just have to go to carbon 4, add that C, and we're not quite done there. Remember, each thing needs a total of 4 attachments. So it needs a total of 4 items attached to the carbon. So for each branch, we have to make sure it has a total of 4. So this first group here, this methyl group, needs 3 hydrogens. This carbon here on the end needs 3 as well. This carbon already has 1, 2 here in the middle, so that means it needs 2 more hydrogens. And then this carbon down here needs a total of 3 hydrogens. So this right here, this represents 2-ethyl 1,4-dimethylbenzene. So we've named a benzene structure, and we've also taken the name and produced a drawing for a benzene structure. Now we can also call benzenes, keep in the back of your mind, we can also call these things aromatic hydrocarbons. So we get now to our last couple things of this section, and that is our properties. That is our properties of aromatics. Now they have some unique properties because of their structure, because of that double bond. They have some unique properties that we have here. So the first major property that aromatics have is that they have health risk associated with these aromatics. One of these health risks includes respiratory ailments. Aromatics can also cause liver problems. In addition, they can cause damage to the nervous system. And then the other thing here, early on in organic chemistry, benzene, toluene, xylene were all once commonly used before those health risks were known. Nowadays, since we know that health risk, we use a solution known as acetone. It used to be found quite often in that fingernail polish remover. That is acetone. So the first known health risk of these aromatic compounds were actually discovered in chimney sweeps in Great Britain. And I failed to mention up here that a carcinogen is another health risk of our aromatic compounds, and all a carcinogen is a cancer-causing substance, or it can cause cancer. So in Great Britain here, this was the late 1800s, mid 1800s, they discovered these aromatic hydrocarbons in chimney sweep, and it was actually found when these chimney sweeps would develop cancer. And that particular aromatic compound that caused that cancer in those chimney sweeps was known as benzoprene. Now, what we need to do, what we need to focus on the last portion of this section, is how we obtain our hydrocarbons. So we need to talk about the main sources of where we get our hydrocarbons. So one of the first main sources of hydrocarbons is going to be from petroleum. And this petroleum is obtained from fossil fuels. Now, these fossil fuels, what actually happens, they were the remains of microorganisms that lived on Earth, and over millions of years ago, they came under tremendous heat and pressure. And what happened is those microorganisms, what they did is they broke down, they transformed into that oil-rich shale and natural gas that we get today as fossil fuels, or our main source of petroleum. So now that we have a background about where these hydrocarbons can come from, we need to take a few minutes to talk about, well, what happens when we actually get those hydrocarbons out of the Earth's surface. So our last bit here is just going to talk about, well, how do we refine those hydrocarbons, And then how exactly, once we refine them, what do we do with that process? So we start out here with this term known as fractional distillation. So fractional distillation is defined as the process that separates petroleum into simpler components called fractions by boiling the petroleum and collecting these particular fractions. So this process of fractional distillation, it occurs after they actually extract the petroleum out of the ground with those big oil rigs, either on land or off of those coasts. And what happens when they extract that oil is there's several different types of hydrocarbons contained within that petroleum. So what happens is they ship these things to refineries, and in the refinery what they do is they put that petroleum through fractional distillation. So to give you an idea here of how this fractional distillation works is this. So in this big tank here on the left hand side, we have the petroleum that's extracted by the oil rigs. And what happens here is they heat it up in this tank. And as they heat it up, what happens is based upon these boiling points, we will get different hydrocarbons to break off. Now, I'll go over the steps here, but the first thing that we have to remember is that this is a process, or this is something that occurs in a series of steps. So the first step is that the raw petroleum, or what we call crude oil, is going to be heated in that large tank to almost 400 degrees Celsius and then transported to that small, skinny, tall tower known as a fractioning tower. Once inside that fractioning tower, what happened is the crude oil is cooled and then it's separated by the molar mass and boiling points. Now, another method to obtain different hydrocarbons is a process known as cracking. And what this cracking is it's defined as the process in which heavier fractions are converted to gasoline by breaking their large molecules into small molecules. Now, what this cracking does is it helps meet the demand for heavier hydrocarbons such as gasoline that you put in your automobile. Now, gasoline is a unique substance, and it's actually not a pure substance. It's a mixture of alkane hydrocarbons with 5 to 12 carbon atoms. Now, gasoline, what happens here with the gasoline fractions that we get from cracking, it is distilled from petroleum, and then what happens is that it's modified in a way that adjusts its composition and adds some substances to it. So what happens here is we get the gasoline from the cracking process of our crude oil, and then what happens is they take that product and then they modify it. They add some things to that item that is cracked, and when they add it, they actually make or produce that mixture of gasoline. Now, I'm out of room here, but I want to talk about one additional thing with our gasoline. So I'm going to shift gears here. I'm going to add another, just a blank sheet of paper. This is just a continuation. And I just want to talk real briefly about our gasoline octane rating. So the first thing that I want to say here is that when you see an octane rating at the gas pumps of a gas station, it's not actually octane that is added to the petroleum you put into your car. It's actually a substance known as 2,2,4-trimethyl pentane. Now, that is oftentimes 2,2,4-trimethyl pentane is often also known as isooctane, and so that's where that octane rating came from. And so the way that we rate our gasoline or our octane rating is this: a rating of 0. So if you see on the pump, which you shouldn't, a rating of 0, that is purely heptane. And then a rating of 100 is purely 2,2,4-trimethyl pentane or isooctane, 100% of that substance. And again, that 2,2,4-trimethyl pentane is known as isooctane, and that's where that octane rating comes from. So to give you an example here, if you go to the gas station and you select a gasoline with a rating, an octane rating of 90, that 90 octane rating at the gas station, what that means is that you have a mixture of 90% isooctane and the other 10% of that mixture is heptane. So if you were to get a gasoline with an octane rating of 85, you'd have 85% isooctane and then the other 15% heptane. So that's how they rate the gasoline when you select it at a gas station. Now, this does conclude section 5. It actually concludes section or chapter 22 with an intro to hydrocarbons. There's been a lot of information, a lot of new information probably thrown at you. So I hope you have enjoyed these series of videos that intro hydrocarbons. And as always, never forget to hit that big thumbs up like button, and never forget to also subscribe.